To carry out the stability analysis, or to introduce it, I need to just introduce another short story. This one is about a Greek mathematician called Archimedes, and who lived about 200 years BC. And at one stage, he was tasked by the king to prove that his crown was made of solid gold and not an alloy of gold and some cheaper metal. Now, Archimedes struggled with this problem until one day, when he was sitting into his bathtub, he realized that the volume of water displaced was equal to the volume of his body immersed in the water. He realized that he could use this principle to solve the king's problem, and so excited was he with his discovery that apparently he jumped up when running down the local town naked, shouting "Eureka," which meant "I found it," or "I discovered it," and has become an expression for a great scientific discovery. So essentially what he done was he immersed the crown in water, was able to calculate its volume. Then he was able to weigh the crown, and from that identify its density. He was able to do the same thing with an equal volume of solid gold nugget, and from that was able to determine that the crown was actually an alloy with some cheaper material in it. So an extension of the Archimedes principle is that if you immerse a body wholly or partially in water, it is buoyed up or supported by a force equal to the weight of the displaced volume of water. And it's that principle that we use in our stability analysis. So for the stability analysis, we need to know the weight of the boat and the center of gravity. In SolidWorks, they refer to that as the center of mass. We'll assume it's the same thing for the purpose of this project. The center of gravity is the center of mass with gravitational effects taken into consideration. We also need to know the center of buoyancy and the buoyancy force and the metacenter. They are all explained in this YouTube link here, but I'll explain in my own words now. Okay, so first of all, you need to design your boat, apply a material type to it, whatever you've printed it from. And once you do that, you can open up this panel, Tools, Evaluate Mass Properties. You'll get the volume, the mass, and the density in the surface area. If you go to Insert Reference Geometry, you'll get the center of mass icon appearing in the tray here. And when you click on it, you'll get the symbol appearing on your boat, and you'll get its coordinates in this panel as well. So the weight of the boat is essentially acting downwards through that point, that center of mass or center of gravity. When it comes to the center of buoyancy and the buoyancy force, if you can imagine a solid version of your boat, so if you've shelled it, unshell it, so it's solid. Then offset a plane at a distance you think the waterline exists, and split your boat at that point and deal with the volume below the surface of the water. Now apply a material type of water to that, so it gives it the weight of the water. And once you get the mass of that displaced volume of water, that's the buoyancy force acting upwards. If it equals the weight of the boat acting downwards, then you've correctly estimated your waterline. If not, you'll have to move your waterline up or down accordingly. There is a slicing tool that you might find useful. It may just be a case that you just need to slightly adjust your plane. So that's the buoyancy force acting upwards. If you get the center of mass of this volume here, that will give you the center of buoyancy. If you're dealing with a ribbed assembly, one tip would be that you could create a series of sketches and loft one sketch to the other to get the general solid shape of your ribbed assembly. Okay, so what we have now is we've got the weight of the boat acting downwards to the center of gravity. That is supported or kept up by a buoyancy force acting to the center of buoyancy to keep the boat at that position in the water. So what happens if we were to tilt the boat right or left? Well, that's where the metacenter comes into play. So what you do is you tilt your boat 30 degrees to the right or to the left. So if you call up your center of mass again, then go into Insert Features, Move, Copy, and Rotate about the center of mass. You'll have to redetermine that water line. You'll see that the shape of the displaced volume of water changes. So your center of buoyancy will shift to the side. Once you calculate that new center of buoyancy, draw a line straight up until it intersects the axis of symmetry. Where it does is your metacenter. And the distance between your metacenter and your center of gravity is the metacentric height. And if your metacentric height is positive, in other words, M is above G, there will be a restoring or righting couple wanting to correct that boat up into its upright position again. If M was to coincide with G, then the boat would stay where it is, tilted in the water. And if M is below G, then the boat will topple. So you basically have to do this with your boat design, but you also have to take into consideration the pump and the battery pack as well. Okay, this guy is called Charles Plimsoll. He was a 19th century English politician. He came up with the concept of the Plimsoll line. And the Plimsoll line is simply a line that's drawn on the side of a boat. And as you start adding weight to the boat sinks deeper into the water. And when it comes up to the Plimsoll line, you can't add any more weight to the boat. Otherwise, you'll affect its stability and it could topple. So that's the project. The information for the project is up on Loop, and you can have a look through that. So reach out to your team members as soon as possible. And I'll be moving around the rooms on the Thursdays to give you any direction that you need. SB32 will be available for you to have a look at, and previous designs, look at the previous designs and their test section as well. And I'll be moving around that room as well. The very best of luck. The teams in the past all seem to enjoy the project very much, and I hope you do too.